Let's take a look at the next example. Let's take a look at example 6. Suppose we want to find the Laplace transform of f of t, where f of t is expressed using a bunch of unit step functions. So here we're trying to find the Laplace transform of 2 minus 3 u of t minus 2 plus u of t minus 3. We know that the Laplace transform is linear, so we can split this apart. This is going to be equal to the Laplace transform of 1 times the constant 2 minus 3 times the Laplace transform of u of t minus 2 plus the Laplace transform of u of t minus 3. We recall that the Laplace transform of 1 is simply going to be equal to 1 over s. That's one of our basic Laplace transforms. So for this first one, we just simply get 2 times 1 over s minus 3 times, now we can think of this as being 1 times the unit step function t minus 2, and we saw from just a moment ago from our translation theorem that this is going to be e raised to the negative 2t, excuse me, times 2s, I should say, wrong variable, e to the negative 2s times the Laplace transform of our function, which is simply 1 over s, plus, again, if it helps, you can think of this as 1 times the unit step function of t minus 3. That translation becomes an e to the negative 3s, not sure why I want to write t all of a sudden, but e to the negative 3s times the Laplace transform of 1, which is 1 over s. So altogether we get 2 over s minus 3 over s e to the negative 2s plus 1 over s e to the negative 3s. So that would be our Laplace transform in example 6 of something that has a unit step function in it. Let's do a couple more of these. Let's kind of get some more practice with these type. Let's take a look at example 7. We'll do a couple more. Let's see if we can find the inverse Laplace transform of the function 1 divided by s minus 4 e to the negative 2s. So now we're going to be working backwards. And so in order to do that, let's state the inverse of our previous theorem. So the inverse form of our previous theorem, remember that was 7.3.2, is going to be of the following. So remember, f of t, notationally, we say that f of t is the inverse Laplace transform of f of s. Then in this case, the inverse Laplace transform of e to the negative as times f of s, this is going to be equal to f of t minus a times the unit step function of t minus a. It's just literally the reverse of what we had. You could apply the inverse Laplace of both sides of that previous statement, and this is what we would end up with. Okay. So let's kind of go ahead and work this one out. So if we look at 1 divided by s minus 4, right, and we have this e to the negative 2s here. So we know what's going to happen with this thing. This is going to produce the unit step function of t minus 2. And then we have to kind of recall what's going to end up with it. Well, the thing that we get with it is f of t minus a. So this is going to be the inverse Laplace transform of 1 over s at t minus a. And that should give us e to the 4. So the inverse Laplace of 1 over s minus 4. We know that that would be 4s. But because of the shift, we have a 4 times t minus 2. So there's our first one. do one more of these. Let's take a look at the inverse Laplace transform of s divided by s squared plus 9 times e to the negative pi s over 2. So once again, we see that we're going to have another inverse here. If we look at the form of this thing, so this is 9, which is 3 squared. Typically, this would be the cosine of 3t, usually. But we have this e to the negative pi over 2s. That's going to provide a unit step function. It's going to look like t minus, the thing that's with the s is pi over 2. So it's going to be minus pi over 2. And therefore, the variable we get inside of our 3 times the variable part is going to be t minus pi over 2. So that's going to be our inverse Laplace transform for this one. We will state one more result before looking at another one, and it's going to be the following. So an alternative form that's very useful and comes up very frequently, an alternative form of theorem 7.3.2 talks about the following. I will not prove this one. You can do it on your own. It's not that hard. But let's suppose we have the Laplace transform of g of t times u of t minus a. Another way that we can write this is as e to the negative as, and then the Laplace transform of the shift g of t plus a. Let's get some practice with this form. Let's take a look at example 8. Suppose we're asked to do the Laplace transform of the cosine of t times the unit step function of t minus pi. So according to what we just said a moment ago, this is going to be equal to, and actually before we do that, so for this, let's see how this kind of fits in here. So I don't want to rush this one too much. Here we see that t, the a is played by the role of pi. So according to this, this should be equal to e to the negative pi times s times the Laplace transform of, now it's going to be the cosine of t minus pi. That's going to be t plus pi, because we have a plus sign in. Minus sign there corresponds to a plus sign there. So we get this. One of the things that you could very quickly figure out, if you wanted to, if you use the identities from trigonometry, you could use the sum cosine formula. Or you can think of this as kind of like a shift of pi for the cosine. But essentially what this is going to be equal to, you can show that that's going to be the same thing as the negative of the cosine of just t. So from trigonometry, it's easy to show that the cosine of t plus pi is simply equal to the negative of the cosine of t. We can then pull the negative out because we know that the Laplace transform is linear. So we get negative e to the negative pi s times the cosine Laplace transform of t. And this is simply going to be equal to negative e to the pi s. And that gives us s divided by s squared plus 1. And I'll probably put the polynomial part out in front here. But this is our Laplace transform of cosine of t times the unit step function t minus pi, and we kind of found this one by using the alternative form of theorem 7.3-8.